Thank you, Peter. My name is Nadia Walker and I will be your room host. My role today is to introduce the fabulous presenters that we have and the sessions and provide any announcements as they pop up. Like you, maths is my passion. Unfortunately, IT is not. So if you have any technical issues, please check your confirmation email for troubleshooting and who to contact for support. On most of the pages on the website, there's a little pink chat balloon. That's the best way to get some IT support during the day if you need it. So let's begin. This is room 3, and our keynote presenter for this morning is James Tanton. James is coming to us from Phoenix. But before I pass over to you, James, I'd like to introduce Penny Addison from the Victorian Department of Education and Training, who are sponsoring our keynote today. Thanks, Penny.
Hi, I'm Penny Addison, the Director of the Curriculum and Assessment Branch at the Department of Education and Training, and it's my great joy this morning to introduce you to James Tanton, who is going to be delivering a keynote address. James is very interesting to myself and to my colleagues at the department because he focuses his work on mathematics being everywhere and for everyone, and mathematics being fun and something that can inspire in all of us this sense of wonder and awe. And, you know, funnily enough, for the work we do, when people often think about mathematics, this is the last thing they think about. We know that lots of kids get anxious about mathematics, and sometimes our teachers do. So, you know, James's work is really interesting because it paints a picture of the light on the hill of what mathematics can be, potentially if we approach it a little bit differently. One of the other things that we really love about James' work is really thinking about how we can be more discerning about our curriculum choices. And I think, you know, this resonates very strongly with some of the work that we are exploring, which is not all parts of the mathematics curriculum are equal. And we can certainly pick out the bits that are core to the learning progress and really focus relentlessly on those. And hopefully, you know, through some of those pedagogical choices and other design choices, make it fun and engaging for learners, which is very, you know, important in the affective domain. But equally, you know, get that deep learning and that deep conceptual understanding. So it is with great pleasure that I introduce James to you today, and I'm sure, and you also will really look forward to his talk.
Well, hello, Victoria, all the way from Phoenix, Arizona. What an honor to be here today to speak to my homeland. I'm an Aussie that lives in America now. I've been here for 32 years, believe it or not. Came over to get my PhD in mathematics way back in the late 80s, and here I still am in the US. But what a joy to be speaking to my homeland today. So thank you so much for having me today, a real honor. And we're also going to be talking about this thing called exploding dots. I'm going to make this a fast-paced hour. So I understand we have an audience that's ready for a gained action in mathematics. We're going to have action in mathematics today. This thing called exploding dots has actually become a bit of a global phenomenon. In fact, you can see on my screen right now, this photograph. This is from Tanzania. This was taken, I think, last year of a student actually playing with exploding dots on a great big chalkboard. I'm going to go through the entire story of this exploding dots experience, which really starts with how we think about and write numbers. I'll go through all of primary school mathematics. Why not? We're here for an hour. We've got plenty of time to go through all the primary school mathematics to show how that connects then to high school mathematics and beyond and beyond. And just to give you a context for this, so I actually, you know, came to America, got my PhD in mathematics, and I did the whole university thing for a while. But then I got sort of very much interested in the state of mathematics education in the US. And I decided actually that the real story of mathematics is missing from the curriculum, the human story, the human joy, the human passion for mathematics, that I actually decided to become a high school teacher to show that human joyous passion for mathematics that I experienced myself going through mathematics in my own studies. And I remember being stuck with a conundrum one time. I was teaching algebra to upper students, year 11, year 10, year 11, somewhere like that. I was being asked to teach them to divide polynomials. My first response to that was, why? Why do you want to divide polynomials? As a research mathematician, I don't ever remember dividing polynomials. I could figure it out if I had to, and that was the key. I could figure it out if I had to. And I realized that's the point of the curriculum. So much of the content in the high school curriculum, it doesn't really actually have immediate application for what everyday living in life. It's more sophisticated, more specialized at that point. So what we really need to do for our students is teach the process of thinking, using content as a vehicle for teaching thinking. So when I was teaching my students dividing polynomials, we didn't need to know how to divide polynomials, but it was a beautiful story for teaching thinking and problem solving and confidence in problem solving. So actually, I invented the story called Exploding Dots. This has since become a bit of a global phenomenon. I don't know why, but it's really the story of place value as it sweeps through the entire early grades, primary school, middle school, high school, college level, university level mathematics, and beyond. So we have, we got 1 hour and 2 minutes, I see, together to go through the entire story of Exploding Dots. And I'm going to ask you, are you ready for it? And the answer I'm just going to tell you is yes. The answer is always yes today. You are ready for it. Actually, but before I begin, I've got one very important piece of business to do. Okay, for those that may have seen me yesterday know what I'm about to do, but this is important. Is everyone in Melbourne, in Victoria, in fact, aware of an international salute to mathematics? Did you know there's an international math salute? Now, I can't see your chat, so I'm assuming the answer is yes, but I have a feeling some people are shaking their heads, no, you don't know the math salute. There really is a salute to mathematics. I'm going to teach it to you right now. Watch out, it's weird. It's a weird salute. But I'm not making this up. If you Google International Math Salute, you will find this. Okay, so it's the morning for you, so put down morning tea, morning coffee, and all the rest. It's the afternoon for me, so I've got my afternoon stacked down, because you need your arms completely free for the salute. So everyone's going to do it with me. So you put your arms out front. Everyone try that. Make your hands look really big on the camera. It's kind of weird. All right, so then for the salute, you go right hand over left hand. That's the hard part, right over left. Then the salute goes palm to palm. Okay, and then it gets weird. You wiggle your little fingers. Then you wiggle your thumbs. Are you doing it with me? Then you wiggle your little fingers again. And then when you're ready, just come on back. Whoa, whoa. What did I just do? What did I just do? But I'll do it again. But I'll try it from a different angle so you can see it from a different angle. So I'm not cheating here. There's no cheating going on. It really is arms out front. That you can see them on camera. I think I'm on camera still. Yeah. Right hand over left hand. You see it's my right hand over my left. And you go palm to palm. You wiggle your little fingers. You wiggle your thumbs. You wiggle your little fingers again. Then when you're ready, just come on back. Golly gee, I wish I could see you. I wish I could see you. Are you doing it? Maybe some people are doing it. Maybe some people aren't. Maybe I need to give something away here. Maybe I need to help you out. Would you like me to give you a hint? Well, the answer is yes, I'll give you a hint. Actually, but no, basically some people aren't saying because they like the problem solving. I'll give half a hint. Here's my compromise. I'll give half a hint. This, I know, seems like a gimmick. I know I'm just playing games right now, but actually it's a very good, important maths lesson of what I just did. It's a very good strategy that mathematicians use all the time. I've given you a problem. Yes, the problem is how do I do this math salute? Actually, I've given you a very special problem. You know what the final answer is meant to be. It's meant to be this. Your arms sort of back to normal. That's the final answer. So here's a very good strategy in maths and life. You've got a problem and you know what the answer is meant to be, or you think you know what the answer could be, start with the answer and work backwards. It's a very simple idea, but it's an extraordinarily powerful idea. It's so simple people forget about it, but it's what mathematicians do all the time. So let me help you out. So let's see, let's start with this answer and see if we can reverse engineer this. Can we do this backwards? So you say to yourself, okay, if that's the answer, where did this come from? Well, it must have come from my hands being turned over. Okay, great. Now you ask, where did this come from? Well, my fingers were curled together. They must have come from my fingers being not curled together. Must have come from that. So now, I bet you're feeling something very strange. This feels really weird and awkward. We started at the end, and we came to this funny feeling middle position. All right, so that's half my hint. I've half helped you, because now your challenge is, can you now start at the beginning and somehow get to that same funny feeling middle position? Because then you'll be set to come back. I've half helped. All right, so here's the deal. So while I'm being particularly boring for the next 58 minutes, you can secretly practice this off camera just to amuse yourself. And then at the end of when I do questions or something like that, feel free to ask me questions if you're truly stuck and this is bothering you. Because now I want to start the story of exploding dots, this global phenomenon. We've counted 6.4 million students and teachers across the planet have played with this joyous piece of mathematics. It's curriculum relevance, curriculum mathematics. It's the power of the human joy of maths in its own right. And it all begins with a story. And it begins with a story that's not true. Here's how my story begins. When I was a child growing growing up back in Adelaide, Australia, I invented a machine. Not true. And all my machine was a row of boxes that go off to the left as far as I please. I could have 100 boxes to the left, I could have 1,000 boxes, I could have 4 boxes to the left, as many boxes as I want. And being a somewhat precocious, strange child, I gave this machine a very strange name. I called it a 2-1 machine, written in a funny backwards way. I'm a young child, didn't know any other way at the time, so I wrote 2-1 backwards like that. And the idea of this machine is you always put in dots. If I put in 1 dot, well, dots will always go into the rightmost box. Zoom. Not very exciting, because 1 dot will stay as 1 dot. If I put in a second dot, dots always go in the rightmost box. Zoom. Then something exciting happens, because whenever there are 2 dots in a box, they explode, kaboom, disappear, and are replaced by 1 dot, 1 place to the left. 2 dots became 1, hence the name 2-1 machine. Get it? So I'm now going to say the code for 2 dots is nothing, 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 1 dot, 0 dots, 1 dot, 0 dots. Here comes the third dot, always the rightmost box, zoom. Okay, the code for 3 is nothing, nothing, nothing. Won't bother writing nothings, but I'll write 1, 1. The code for 3 in a 2-1 machine is 1, 1. I have a feeling putting in a 4th dot is going to be particularly exciting. Here it comes. Zoom. Always the rightmost box. 2 dots, kaboom. Dot. 2 dots, kaboom. Kabow. Fabulous. 4 had a double explosion, and it's now 1, 0, 0. The code for 4 is 1, 0, 0. 5, put another dot. I bet you can see in your mind's eye it's going to be 1, 0, 1. I'm going to put it in. Zoom. That was the 5th dot. 6th dot. Can you see in your mind's eye what it's going to be? I'll just pause for a second. Can you see what it's going to be? Because here it comes. Zoom. Kabow. Dot. 1, 1, 0. 13. I've skipped some numbers. In the chat, if you're able to, can you tell me what the secret code for the number 13 is in this 2-1 machine? And Nadia is going to look at the chat, my host, and tell me what sort of answers people are giving, if that's possible, if technology works. We'll find out. I also have to know that we have about a 7 to 10 second delay. So as I'm saying these things, you're not hearing me say it yet. So that's why I'm rambling on as though I've got something meaningful to say, but I don't. Okay, Nadia, you see people write things in the chat at all and able to tell me anything that's being said, what the code for 13 might be? Find out. We also know that we have about a 7 to 10 second delay. As I'm saying these things, you're not hearing me say it yet. So that's why I'm rambling on. In fact, I'm hearing my own voice. There is a delay. Wow.
Hi, James.
What's the code for 13 in this 2-1 machine?
We've got a couple of responses in there, James.
Like what? What sort of things? Fabulous.
Someone has considered 1,000.
1, 0, 0, 0. Okay. Anything else?
Someone has considered 1,101.
1, 1, 1, 0, 1. Okay.
Well, there's quite a few of those actually.
Oh, okay. Times many. Okay.
Someone has considered 1,000.
Okay. Oh, but yep, we have got it. I can even hear our own voices delayed. Okay, we've got a serious. Okay. All right. Brilliant. You guys are thinking. So I know you're there. I've got an audience. Woo! Thank you for coming along today. Okay, so it's interesting. So we've got 2 answers, and this seems to be a popular answer. I'll tell you what my response is. Here's my honest answer. I think it's hard. I think this is hard. So I'm going to say, no, let's stop. Let's have a break from this 2-1 machine. Let's just have some fun. Because I actually, in this story, that's not true, had an epiphany. Because I realized one day, instead of doing a 2-1 machine, I could actually change it up and make it a 3-1 machine. 3 dots explode to become 1. Whoa, whoa. Put in 1 dot. Here it goes. Always the rightmost box. Zoom. Stays as 1 dot. Put in a second dot. Always the rightmost box. Here it comes. The right. Zoom. Oh, but 2 dots stay 2 this time because I need 3 dots to explode to become 1. So 2 has the code of 2. It's not until I do a 3rd dot. Here it comes. Whoops. Zoom. 3 dots explode. Kaboom. Become 1 dot. 1 place to the left. 3 become 1. Code is nothing, nothing, nothing. 1, 0. Okay. 4. Here it comes. Zoom. 1, 1, 1 dot, 1 dot. 5. Here it comes. Zoom. 1 dot, 2 dots. 1, 2. 6. Can you see in your mind's eye what it's going to be in this 3-1 machine? I'm pausing for just a moment. Because here it comes. Zoom. 3 dots explode. Kaboom, become 1, 2, 0. Okay, I'm going to skip some numbers. What's the code for 13 in a 3-1 machine? Maybe in chat we'll collect some answers, because you probably guessed what my answer is. So just wait for the video delay to do its thing. Then a chance for people to think and type things in, and we'll see what we get. Oh, we maybe have a lot of delays. Is the chat working, Nadia, or is life changed on us?
Might have them stumped on this one, James.
Oh, good. The answer, you're right. The answer is hard. I'm with you. Yes, good for being stumped, because I agree, it's hard. Crazy. All right, if it's hard, let's not do it. That's my answer. If it's too hard, don't do it. But then I realized I had another epiphany. So if doing a 2-1 machine or a 3-1 machine, I could do a 4-1 machine, or I could do a 5-1 machine. In fact, let's go really crazy. Right now, since we're all together here, let's go all the way up to a 10-1 machine. And let's be absurd. Let's put in 273 dots in a 10-1 machine. What is the secret code for the number 273 in a 10-1 machine? Whoa. Now that seems hard. That really, truly seems hard. So here's what we're going to do. We've got plenty of time together. We've got another 52 minutes left together. I'm going to actually do it. I'm going to put in all 273 dots right off the bat. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 19, 20. So here we go. So we've got lots of time to watch me put in 273 dots. As soon as someone types into the chat that I've got enough, you just have to say stop. I'll believe you it's 273. So that gives me plenty of time, because I know there's this 10-second delay. So I've got 10 seconds of doing this until someone tells me otherwise. Maybe Nadia will tell me otherwise. James, stop. That's 273. Maybe Nadia will save us.
Lots of people have said 273, James.
Is that it? We're done. Okay, thank you. That's so correct. That's exactly 273 dots. I'm so impressed. Well done. Okay, so let's think our way through this. Let's think our way through it. I'm just doing like basic maths right now. First question, will there be any explosions? Yes or no? Or 10 dots explode, become 1. There are lots of groups of 10 in there. There's going to be lots of explosions. Yes. Next question, how many explosions will there be initially? My camera's a little bit out of focus. Come on, camera. We say, okay, how many groups of 10s are there? Well, there's a 10, there's a 10, there's a 10. In fact, you can see in 273 dots, there'll be 270 dots, 27 groups of 10. There's going to be 27 explosions. Kaboom, kapow, kazing, kazoop, kadoop, kadoop, kadoop. Lots of explosions. Lots of things explode away. Or any dots left behind? Yes. I'm sure you're thinking there'll be 3 dots left behind. I don't know if you can see them. I'll do them big dots like that. 3 dots left behind, 27 explosions. Each explosion makes a dot, which means 27 dots will appear there. I'm getting very tired of drawing dots. Can I just write 27 for 27 dots? Yes, the answer is yes. All right, the answer is always yes today. All right, next thing. Any more explosions? Or 10 explode to become 1, so 2 groups of 10 in there would leave 7 behind. 1, 2, 3, 4, 5, 6, 7. And 2 explosions, kaboom, kadot. Bingo. That's it. So the secret code for 273 in a 10-1 machine is nothing, 2 dots, 7 dots, 3 dots. The secret code for 273 is 273. And I have a feeling you guys are now completely onto me. You might know what's actually going on at this point, because that seems awfully familiar. In fact, I have a feeling you guys were onto me very early on, way back at the 2-1 machine. Let's think our way through this. What's really going on? Well, if the game was that I always put dots in there, a dot there is always worth 1. What's a good color? I'll do it in green. Dots there are always worth 1. And then I said, okay, 2 dots, 2 1s, kaboom, make a dot there. So this dot is really worth 2 1s. It must be worth 2 1s, which is 2. And 2 of these, I had 2 dots there, 2 2s would explode, kaboom, and make a dot there. This dot must be worth 2 2s, which is 4. And 2 dots here, kaboom, 2 4s makes a dot there. That dot must be worth 2 4s, which is 8. And 2 8s make one of thems, which is 16. 2 of thems make them one of the next ones, 32s. And 32s times 2 will be 64s, the next box, and so on and so on. So it looks like we've got the doubling numbers, the powers of 2 here. And look at this. Many people said the code for 13 was 1101. You said 1 dot there, 1 dot there, 1, 1, no dots there, 0 dots there, and 1 dot there. Can you see, and I mean literally see, that 1101 is correct? That is the correct code for 13. One of these, don't use any of those, and one of those. An 8 and a 4 and a 1 does make 13. You're absolutely correct. Welcome to base 2. Welcome to binary. We've just discovered how to write numbers in terms of the powers of 2. We're writing numbers in binary. Brilliant, brilliant. Okay. The hard has now become manageable. I love it. So where's that 3-1 machine? Let's do the same thing there, because we did not work out the code for 13 on the 3-1 machine. That was hard at the time. But let's think our way through it. Dots there, always worth 1. And then we said 3 of these. 3 1s, kaboom, make a dot there. That must be worth 3 1s, which is 3. And then we said 3 of these, 3 3s, kaboom, make 1 of those. That must be worth 3 3s, which is 9. And 3 of these, kaboom, what makes 1 of them's? 3 9s is 27. And then 81, and then 243, and then 729. That's as far as I feel like going. All right, okay. 13. Is it hard or is it manageable now? What is the code for 13 in a 3-1 machine? Can we now see it? And maybe this is worth putting in the chat. As I gulp some drink. What would 13 be? And I can see Nadia looking at the chat. We might be having people come up with the answers. So in bated breath, waiting here. Anticipation is grand.
We've got lots of people with 111, James. How does that?
Of course it is. I can see that too. 1 9, 1 3, and 1 1 doth 13 make. 13 has the code 111. Welcome to base 3. Welcome to ternary. This is brilliant, base 3. Love it, love it. And then of course, look what's going on in this one, which I think you are onto me. In a 10-1 machine, same game. Dots there are worth 1. 10 of these make 1 of these, must be worth 10. 10 of these make 1 of these, must be worth 100. 10 hundreds make 1,000. 10,000 make 10,000, and so on. Welcome to base 10. Welcome to base 10. In fact, you can see that actually we literally had 273. In fact, if I write it out, literally 273. We literally speak base 10, 200. There they are, 200s. 7T. In English, that TY is short for 10. Look at them, 7 10s. There they are. And 3 1s. We speak base 10. Welcome to the number system that we choose to use today. Actually, that's a good question. Why do you think we humans are obsessed with the number 10 on matters of arithmetic and counting? Why do we like base 10? Why do we humans like the number 10 so much? So rather than wait for the delay, I have a feeling I can give away the answer because you might know this. We humans are obsessed with base 10 because of these things. We have fingers and thumbs on the end of 2 hands. In fact, we have 10 of these things. We have 10 of these things. We think they're really good for counting on. And we call these things not just fingers and thumbs, we call individual ones digits. Have you ever noticed in math class, we call individual numbers within a longer number, we also use the word digits? It's not a coincidence. We humans are so obsessed with the number 10 because of our physiology. Though I have to say, some cultures actually did go base 20. Base 20. So why would some cultures go base 20, do you think? You think about it for a while, and I bet you're saying it. They must be thinking not only their fingers, but if you look down, they must be also thinking of their toes. Fingers and toes. Some cultures went base 20, probably because of counting on fingers and toes, at least mentally. In fact, actually, we have vestiges of base 20 left in our society today. So I've said I'm living in Phoenix, in America. The Americans had a very famous president called Abe Lincoln, who gave a very famous address called the Gettysburg Address that begins this way. It's 407 years ago. That's all I know of it. I don't really know my American history. But my question is, in this very famous address from the 1870s, I think, golly gee, when was it? Well, my question is, he started 407 years ago. My question is, How many years ago is that actually? What is 4score and 7? How many years is that? You think about this for a while, it takes a little moment to realize that actually Abraham Lincoln was speaking base 20 right there, because score is an old word for 20. Score is an old word for 20, so he's actually saying 4 20s and 7 years ago, 87 years ago. He spoke base 20 right there. And actually, I happen to know someone who I can see speaks a little bit of French. In France, how do you say 87 au français? Because the French have a little bit of base 20 in their language as well. So Nadia knows some French. I don't know French, but I believe 87 au français is 87. Did I get that kind of right, Nadia? Please say yes. Yes, I got the thumbs up. And which is literally 4 20s, 7. They're speaking base 20, just like Abraham Lincoln did. So even to this day, some languages have vestiges of base 20 in their languages. Actually, I'll tell you, some cultures even went base 12. 12? Where did that come from? That's an odd one. That's really weird. And actually, you might see this with some of your students to this day, because people actually did realize, and still today, to this day realize, there's a very natural way for us humans to count to 12 on one hand. We've got 4 very long fingers, each naturally divided into 3 sections, and a very handy pointer, this thumb. And you might see some people count like this. It's very popular in parts of India and Southeast Asia, still to this day. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In fact, that was one group of 12, mark on my left hand. The second group of 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Up, second one. Third group of 12, up. Actually, you can count 12 groups of 12 on your 2 hands. You can count to 144 on your 2 hands. Very clever. And some cultures probably went base 12, maybe because of that. Very interesting. All right, so maths is very much a human pursuit, a very much joyous human pursuit, lots of human answers to these things, but I'm going to be our Western human selves. We seem to live in a society today, oh, there it is, that is obsessed with base 10. I will now whip through the entire primary school curriculum in base 10. Because I'm a high school maths teacher, remember, I'm actually doing high school maths. And what I'm doing with you today is literally what I did with my high school kids to explain why we divide polynomials the way we do. This all will make sense as a high school teacher because it's really the story of place value. We've just discovered place value, how we write and think about numbers and how we visualize numbers. The visuals of the count is the key thing. All right, so let's do it. Let's get primary school maths out of our way. So you've learned how to write numbers now. What's the first mathematical operation you might actually do with numbers is addition. So let's do some addition right now. And I can do something like 142 plus 233. Great. And the answer is clearly, without any work, is 375. Now, I went fast. I don't know if you noticed anything strange about what I just did then. Did you notice I went left to right? 1 plus 2 is 3. 4 plus 3 is 7. 2 plus 3 is 5. I got 375, which I believe is correct. It's not what I was taught back in my days, back in Adelaide, Australia. I was taught to go right to left, which I, as a kid, actually thought was very strange because I was being taught to read left to right in every class except maths class. Okay, don't know why, but I obeyed. I was a good student. So if you go right to left, you get the same answer? Well, yes. So what's the diff? Why? Why bother going left to right or right to left? It's the same answer. And I bet you're saying, James, don't be silly. That's just too nice a problem. Maybe I should make it like 157 plus 275. Okay, this is more fun. 1 plus 2 is 3. 5 plus 7 is 12. 7 plus 12 is 12. Oh, there we go. The answer is 312 T12. 312 T12. I'll even draw you a picture that I'm right. This is a 10-1 machine. I said, take the number 157. 1 dot, 100. 5 dots, 5 tens. 7 dots are 7 ones. There they are. There's 157. Please add 275. Please add 200s. Okay, 200s. Grand. Add 7 tens. No worries. I can add 7 tens. There they are. And please add 5 ones. Piece of cake. There's 5 ones. Clearly, I have 300s. Clearly, I have 12 tens. And clearly, I have 12 ones. The answer really is 312 T12. I'm even saying it correctly. 300, 12T, TY for 10, 12. Whoa. So I have a PhD in mathematics. I'm a professional mathematician. There's nothing mathematically wrong with that answer. It's got my stamp of approval. There's my hand on camera saying, I approve as a mathematician. If any student wrote that on exam, full marks from James Tanton. The question is, that sounds weird to society. Society doesn't like saying 312 to 12. They think it's absurd. So just for society's sake, not for math's sake, math is fine with that answer. Society doesn't like it. Just for the convention of society, what number is that really in society? Maybe we should put that into the chat. What number is that? How would I say that number in a way that society would accept? What do people think? I have another glass of my latte here, iced coffee. What number is that really in society speak? Of course, I guess we could actually just do this the standard way, right to left, and get the answer something. What's the answer? I know what it is. I want to know what it is. I'm curious.
432, James.
I'm sure it is, because exactly 10 dots explode. Remember, this is a 10-1 machine, so 10 explode to become 1. So 10 of these dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 explode, kaboom, disappear, make an extra dot there. So that makes 4 dots there. That leaves 2 dots behind. 402 T12. That's correct. 402 T12 is also correct. Still sounds weird to a society, but of course 10 explode here. Kaboom, 10 explode here. That leaves 2 behind, make an extra dot there. So that makes 3 dots. The answer is 403 T2. 403 T2. And English is just weird. You don't let me say 3T. We should say 3T, but we say 30 because English is just weird. In fact, that was my keynote yesterday as I was doing this talk, was more on the primary school maths. We talked about how weird English is. Actually, look at the recording yesterday's talk. That was a good one. So talk about that. That's great. Addition done. We can fix up for society's sake. That's fine. Maths doesn't care. That's a fine answer for maths. This was a fine answer for maths. Everything is a fine answer for maths. It's all good. It's just societal convention. Doesn't want more than 10 dots in a box. Society is just demanding. So let's have fun with it. If we don't have any regard for what society thinks, what's 2684 times 3? What do you think is the James Tanton don't care about society answer to that problem? What is 2684 tripled? And whilst it's coming up in chat, I'll just draw a little picture to show what's going on, because I have to fill in a 10-second delay. What is the James Tanton no regard to society answer to this problem? Good luck typing into chat. I don't know how you're going to type into chat. Be inventive, be clever, be creative. Okay, Nadia's reading things. Maybe things are coming in. I'm poised. I'm ready. I'm quivering with excitement.
Now the pressure's on me, James, to try and interpret what people have written in the chat box.
That's true. That's true. It's your issue. All right. I bet that a lot of them start with a 6. Am I right?
Yes. All the responses so far are starting with a 6. And then we've got some version of a 18, 24, 12.
Okay, great. I agree with that. So
I'm looking forward to seeing what you say that is.
Okay, well, that's the fun part. Okay, this is great because I agree with that answer. Because look at this. I'm really saying take this and triple it. So take 2,000s and 600s and 8 10s and 4 1s and just triple them. And you think about the logic, just common sense says, oh, well, if I've got 2,000s and I triple them, I'm now going to have 6,000s. If I've got 600s and I triple them, I'm now going to have 1,800s. If I've got 8 10s and triple them, I'm going to have 24 10s. Common sense. 4 1s makes 12 1s. So I'm tripling everything. So the answer is this. Now, the fun part is saying it out loud. I'm going to try to say it out loud. You ready? The answer is yes. Here goes. 6,000, 1,800, 24, 12. 6,000, 1,800, 24, 12. By the way, this one did not sound loud, weird to our ears. We do say 1,800 in everyday language. We will allow me to say 1,800. So society is actually fickle. It sometimes let me say 1,800, but it won't let me say 24T, 12. So society is all over the place. All right, so now the question is, this is weird for society. I bet we can fix it up for society's sake. So I'll just do this quickly. For example, I can say 10 dots here would explode. Kaboom, another 10 dots there explode. So 2 explosions. Leave 4 behind and make an extra 2 dots there. So the answer is really 6, 20, 4, 12. 10 dots explode here, leaving 2 behind. An extra dot there makes that 5, 6, 20, 100, 50, 52. Oh, 2 explosions, leaving nothing behind. 8, 8, 0, 5, 2, 8,052. There it is. Beautiful, done, and society would like that. Those societies demanding doesn't let me say 5T. I should say 5T. I have no idea how young kids learn English and maths with words that keep changing on them, like 50. Where did that come from? It should be 5T. Oh well, society is just fickle and demanding. What can I say? All right, we're whipping through it. We've done addition, we did multiplication. Okay, I skipped over this one. Subtraction. This is a speed keynote of all of K-12 mathematics in 1 hour. I don't know if you're hanging in there. Doesn't matter. The answer is yes, you are, because you have no choice. Let's keep going. Subtraction. Here's my trouble with subtraction. I don't believe in subtraction. There is no such thing as subtraction. To me, subtraction is still addition. Subtraction equals the addition of the opposite. There is no such thing as subtraction. Subtraction is the addition of the opposite. Come on, camera. Focus, focus, focus. No technical troubles now. All right, great. Plus, there's also a lecture in hieroglyphics. Good luck reading my handwriting. But here goes. What do I mean by that? So I need the opposite. I need a notion of the opposite, which puts me in a pickle, actually, because right now, everything I've been doing has been about dots. So I now need the notion of the opposite of a dot. I want to talk about opposites, which gives me 2 problems. What should I draw for the opposite of a dot? And what would you like me to call the opposite of the dot? In the chat, this is going to be interesting. What would you like me to draw for the opposite of a dot? That's one question. Another question is, what would you like me to call the opposite of a dot? I'm curious where your brains go on this one. So I will wait out the 10 seconds delay because I want to know what you fabulous guys think here.
I'm quite curious where your brain's gone with this one too, Jane.
Okay, we'll find out.
Let's see.
What would I like to draw for the opposite of a dot? And what would you like me to call the opposite of a dot? What name?
Okay, just one person has said they agree with you. Subtraction doesn't exist. So you've got a convert there.
Excellent.
A couple of people have called an anti-dot.
Anti-dot. You may have seen some videos. Anti-dot. Okay.
A hollow.
Hollow. Oh, we should suggest the picture. Maybe I'll do like a hollow dot. I'll do that. Actually, I'll do that. Let's do a hollow dot for the anti-dot or the hollow. I can call it hollow. Okay, great.
Or just
Any
a
other
circle.
names? Just a circle.
Just a circle. Yeah. A negative dot.
Okay, a neg dot.
Or a square.
That's very literal. Very literal. Okay, excellent.
A
All right,
square.
cool. A square. Okay, so I like that. Perfect. I'm with. Oh, that's a good one. Never heard that one before. I should point something out. When I do this with adults, most adults usually will come up with anti-dot. When I've asked this question of kids all across the planet, doesn't matter which country I'm in, kids invariably say, even if English is not their native language, Todd. Do you see where that's coming from? Because you've got to love kids. Dot backwards. So now we've got a question. Do you want to go with the adult answer question, adult term or the kids term?
James, there's one more.
Oh,
one more in the mix. Sorry, someone said call it a don't.
Don't. Yeah, we're like, do you want the apostrophe or not? Yeah, we'll have the apostrophe. I love that. That's good too. Love it. All right. Okay. Now I'll go with the first one you guys said. You guys said anti-dot. I will go with anti-dot today. So the anti-dot is the opposite of a dot. But it's like matter and antimatter, and in science fiction or maybe actual science. If I take a lump of matter, I take a lump of antimatter, and I bring them together, what happens? Well, I won't say explosions. I've already got exploded. They just like poof. They just annihilate and disappear. So like matter and antimatter, if I take a dot and I add to an anti-dot, the picture I get is, well, poof, that. Like that's the actual picture, nothing. I get nothing. I don't know how to draw nothing, but I don't draw nothing. I just do nothing to draw nothing. So maybe that's the nothing, poof. So dots and anti-dots are opposite each other. So let's take this through. So what is subtraction? To me, subtraction is the addition of the opposite. So something like 276, take away 134 is really this problem. I'll draw a 10-1 machine. All right, 200s, 7 10s, 7t, and 6, 4, 5, 6. Please add, no subtraction, add anti-134, one anti-dot there. 3 anti-dots in the tens place. Please add 3 anti-tens. Please add 4 anti-ones. No worries, 4 anti-ones. Now, what do we get? What do we get? Poof, dot and anti-dot, poof. Oh, dot and anti-dot, poof, poof, poof. 3 poofs right there. Dot and anti-dot, poof, 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 poof. And what am I left with? I'm left with 1 actual dot, 4 actual dots, and 2 actual dots. The answer is 142. It's as though I went left to right again. 2 take away 1 is 1, 7 take away 3 is 4, 6 take away 4 is 2. I tell you, left to right, how we read is in our society. I love it. Maths class should be left to right. So you might be saying, that was too nice an example. Let's do a harder example. I'm with you. I know you're on to me. 413, take away 155. How's that one? All right, left to right. 4 take away 1 is 3. 1 take away 4 is negative. 5 is negative 4. 3 to 5 is negative 2. The answer is 300 negative 40 negative 2. Done. Stamp of approval. No worries with that one. And I'll show you I'm right. I will draw you a picture to convince you I'm right. 413. There it is. 413. Please add 1 anti-100. No worries. Add 5 anti-10s. No worries. Add 5 anti-1s, piece of cake. There they are. Annihilations, poof, poof. Poof, poof. And what have I got here? I've got 3 actual dots. I've got 4 anti-dots and 2 anti-dots. The answer really is 300 negative 40 negative 2. Done. No work. Life is easy. Perfect. Perfect. Just that society, being its demanding self, does not like that answer. So how could we fix that answer up for society's sake? What could we do? What could we do? How do we fix that up for society's sake? I will wait in the chat again. Any brilliant moves we can do right now to make this acceptable for society?
James, just while we're waiting for the chat to catch up to you, someone has said in their comment here, they disappear into a cloud of logic. That's giant feedback.
So poetic and so beautiful. Oh, they do. Off into the ether of wisdom. Love it. What could I do? You're right. Okay, I'm moved by the beauty of that comment. I've also got my question still hanging. What can I do to fix up this mighty strange answer, which is mathematically solid and correct, for the sake of society? Society is so demanding.
Okay, someone said minus 42 from 300.
Oh.
100 minus 42.
Okay. You guys are cleverer than me. Oh, I see what you're saying. Some people are saying this 3 here is really 300. And you're saying this negative 4 here is really negative 40. And this 2 here is really negative 2. So the answer is really what? 260, 258. You actually see it's 258. Okay, that's brilliant. That's way cleverer than me. Because what I was going to do, or play with my picture, I can say, well, hang on. Society doesn't like these anti-dots here, but I've got this dot over yonder. And think about it. This dot must have come from 10 dots over here exploding, kaboom, to make that dot. What if I unexploded that dot? Unexplode it. I'll do a sucking sound for unexploding. Don't know why. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Aha! So that's really 2 dots left there, and I create an extra 10 dots there. Because that 1 dot really was 10 dots in the box before. But now I can do some annihilations. Poof, 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 poof. That's really 6 dots. The answer is 260 negative 2. And I can do it again. Another annihilation. Hang on, that's that one. Annihilate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 1 less dot there, extra 10 there. Oh, poof, poof, 8. There, I saw it too, 258. So I was doing unexplosions as I was going along. You guys were clever at interpreting the answer that was right there. Either way, all good and correct maths, lo and behold, is good and correct. It shocks people. All correct routes to mathematics and correct answers are actually beautiful and correct. Crazy, crazy, crazy. All right, okay, so that's it. We're whipping through primary school. I'm not yet at high school, and we have 22 minutes and 48 seconds left together. Let's keep going. You're on. Addition, subtraction, multiplication, division. All right, so let me cover division sort of backwards, literally, by going back to multiplication for a moment. Whoops, let's make it easy. Oh, my camera's all over the place. 1302 times 3. Come on, camera, capture up. Now, the answer is obviously 3906. All right, but let me think my way through that, because what I did there is I said what we're doing earlier on, draw a picture of 1302, 1 dot, 3 dots, no dots, 2 dots. And I said, please triple everything. So I literally triple everything. This 1 dot will have to be tripled. Okay, tripled. This 1 dot will have to be tripled. Okay, that dot will have to be tripled. And that dot will have to be tripled. Nothing to triple there, but that dot has to be tripled, and that dot has to be tripled. And I really do see 3 dots there, the thousands place, 9 dots, no dots, 6 dots. Okay, so now pretend I didn't show you that original problem. Goodbye, goodbye. Pretend you didn't see that. And I gave you the answer first. I say, can you undo that multiplication? Can I undo it? And you say, well, what's division here? It really is the reverse of multiplication. What got multiplied by 3 to make 3906? What got tripled? And I think my way through this. Okay, this is the answer. What got tripled? Well, I look at this and say, oh, here's a dot. Well, this was a good color. There's a good color. Here's a dot that got tripled. That group of 3 must be 1 dot in the thousands place that got tripled. This is a group here. That's a group of 3. So there's 1 dot there that got tripled. There's another dot there that got tripled. And there's another dot there that got tripled. Nothing there got tripled, but this is a dot that got tripled. And this is a dot that got tripled. Each group of 3 represents a dot that got tripled. So I see that 1 dot in the thousands place, 3 dots in the hundreds place, no dots in the tens place, and 2 dots in the ones place actually got tripled to give me 3906. So I've just discovered division by literally looking for groups of 3 in a picture of 3906. You've got to love it. I love it. You don't have to love it. You've grown adult selves. You can decide not to love it, but I love it. And let's do a harder one, because I'm going to push us hard today and go straight to a double-digit multiplication division problem. 276 divided by 12. 276 divided by 12. How am I going to do this one? Well, we do what I did before. It's 276. Let's start by drawing the answer. Here's the answer. Something got multiplied by 12 to give me 2 dots, 7 dots, and 6 dots. Now 12, so I'm looking for groups of 12, but here's the annoying thing about society. It's really meant to be a group of 12 dots. Society doesn't like me having 10 dots in a box. It won't let me say 12 T, for example. Society wants me to do the explosion and say, actually, no, if you've got 10 dots, 12 dots in a box, 10 will explode, make 1 dot, 1 place over, and 2 dots left behind. So 12 really looks like this. It's 12 dots in a box would be there, but kaboom, some spillage makes 1 dot go 1 place to the left. So 12 actually looks like 1 dot next to 2 dots, even though it should be all 12 dots in 1 box. That's the little annoying thing about society, insisting I do all those carries. Okay, demanding society, what can I say? But let's do it. Can I see any 12s in this picture of 276? Can I see any 1 dots next to 2 dots anywhere in this picture? And the answer is, why, yes. There's 1 dot next to 2 dots. Now, to think about this for a moment, where in that loop are the actual 12 dots? Well, if you think about it, they must all be here in the right part of the loop, because 12 dots must have been here and kaboom, exploded and spilled over. So actually, 12 dots there were right there. There was a group of 12 that was sitting there and spilled over 1 place to the left. In fact, there's another 1 dot next to it. There's another 12 right there, another one at that 10s level. 12 dots must have been here, kaboom, and spilled over. All right, any other 1 dots next to 2 dots? The answer is yes, if you start getting clever, because there's now 1 dot next to 2 dots over yonder. All right, and where are those 12 dots? They must have been right there. They must have all been there and kaboom, spilled over 1 place to the left. Any other 1 dot next to 2 dots? Why, yes, just underneath that one, another one at that level. In fact, I can see a third one. My loops are getting a bit weird now, but there's another 1 dot next to 2 dots right there. So I actually see it was 2 dots at the 10s level that got 1205, and 3 dots at the 1 level that got 1205. The answer must be 2, 3, 23, which I hope is correct. If someone could do that on a calculator, because that's the smart thing to do in the 21st century, if you really want to know the answer, get out your calculator. If I'm wrong, just type into chat, but if I'm right, I'll believe you. All right, gotta love it. In fact, do you want to do one on your ownsies? The answer is always yes. On your ownsies. So I can have another sip of my drink. What is 2783 divided by 23? Draw me a beautiful dots and boxes picture of 2783 divided by 23. Have a go. Oh, I'm in America. Do I say give it a go? Is that Aussie or is that American? Give it a try. Give it a try and give it a go. Whichever one's appropriate for Australia, that's what I'd like you to do.
Someone's just asked in the chat box if you're going to grapple with remainders.
Oh, I think we have to now. Now someone's mentioned it, the answer is always yes. You got yes, of course we have to grapple. Okay. Issues been raised, we will grapple with remainders. I'm up for it. All right, let's give this one a go. We have 16 minutes and 45 seconds left together in our lives, and I've still not yet reached high school maths. You must be thinking, why is this a high school experience for you? It is. I did this all with my kids. I did this with my university kids even. This is high-level maths, believe it or not. Thank you, K through 8, for teaching valid, fabulous high-level maths to our kiddos. You're making my life so much easier as a high school teacher. Thank you, thank you, thank you. All right, let me do 2783 as well. 2, 7, 8. Oh, maybe I should be silent. Probably rude of me to talk while you're doing this. What does 23 look like? Apparently I'm not being silent. Okay, 2 dots and 3 dots. Lots of explosions happen there. So you're looking for 2 dots next to 3 dots in a picture of 2783. I see it. I see there's one group of 2 next to 3 right there. All 23 dots must have been right there, and a lot of spilling, kaboom, kapow. 2 dots next to 3 dots. Yes, over here. Oh, another 2 dots next to 3 dots. My picture's getting awfully messy. And loops are getting awfully weird. Oh, boy, am I nice to you. 2 dots next to 3 dots right there. I think the answer is 121. Brilliant, brilliant. So the question of remainders. Well, if I gave you instead 2784 divided by 223, how would the picture change? How would your interpretation of the answer change? And you realize if there are remainders, you will literally just see them. Literally. 2784. I'd find all my 23s like I did before, and there'd be 1 dot left over remaining. So if I'm doing 2783 divided by 23 is 121, 2784 divided by 23 would be 121, just like I did before, with a remainder of 1. Or if you're being a high school person, you have to say it's really 121 plus 1 dot still waiting to be divided by 23. 121 plus 123rd. You want to go back into fractions. Beautiful, beautiful there. If there are remainders, you'll just see them. You can't not see them. Remainders are going to be staring you in the face. You've got to love it. All right. That's a quick overview of at least the arithmetic of primary school maths. It's time for me to start doing high school maths. Finally, here I am, like 45 minutes into the talk, the keynote for high school teachers, and I've not done any high school maths. Crazy. Here's my point. We are the ones obsessed with this. We're having 10 fingers on our hands, or, we're doing all this in base 10 because we humans love the number 10. We think it's the bee's knees because of our physiology. Though we could do all the maths we just did in computer language. Computers only have 2 fingers, but they have electrical switches either on or off. They've only got 2 states. So base 2 is perfect for computer, and you can do all the maths we just did in computer science. In fact, computers do. Everything we just did works in base 2. It also works in base 3. It works in Martian. I know Martians have 3 fingers on 2 hands. We could do all the work we did in Martian if we want in base 6. Everything we just did would work just fine. You can do it in any base you like. In fact, I'm going to prove that to you right now, that you really can do this in any base you like by doing everything we just did in all bases all at once, right now. Whoa. In 13 minutes and 11 seconds, I'm going to do all we just did in all bases all at once. Here goes. Here's how I'm going to do it. I'm going to play this game again. I'll say we're in a machine. I'm just not going to tell you what machine we're in. It could be a 10-1 machine. I'm not going to tell you. Maybe I'm thinking 7-1 in my brain, a 7-1 machine. I'm not going to tell you. It's the moon I'm in. I'm not going to tell you. Maybe it's 3-1. Maybe it's 14-1. You won't know because I'm just not going to tell you what machine I have in mind. Though, just to give a nod to algebra curriculum writers all across the planet who seem to be obsessed with a certain letter of the alphabet. If you don't know what a number is, they always go to the same letter of the alphabet over and over and over again. I will do the same thing. You don't know if this is a 10-1 machine or a 7-1. I'll call it an X1 machine. You don't know what the machine is. If X is 10 in my head, I'm thinking 10, 1 machine. If I'm thinking this is binary, I'm thinking X is 2. This is a 2, 1 machine. All right, so there's a machine. I'm afraid you really know nothing about this machine, other than I just called it an X1 machine. That's all you know. Actually, that's not true. You do know more. You know that the game we've been playing is that dots here, whoops, there, are always worth 1. 1 dot, 1 dot, 1 dot. And you know, whenever I've got X dots in a box, you have no idea what that number is, but X dots, boom, explode, make 1 dot, 1 place to get over. So this dot must be worth X1s. X1s will be, well, whatever X is, will be X1s is X. And you know, X of these, whatever it is, kaboom, make 1 of those. This dot must be worth X X's, X lots of X, X groups of X, X lots of X. That's X times X, that's multiplication. X times X is X squared. And X of these, whatever the number turns out to be, kaboom, this one must be worth X squareds. X lots of X squared is X cubed, and so on. So you actually know what each dot is worth in terms of X's. And in fact, if I tell you X really was a 10, 1 machine, this is really 10 in my head, are these the correct numbers for a 10, 1 machine? Why, yes. 1, 10, 10 squared is 100, 10 cubes 1,000. Yes. If X is 10 in my head, that is a 10, 1 machine. Or if X is 2 in my head, this is a 2, 1 machine. Yes. 1, 2, 4, 2 squared, 8, 2 cubed. Beautiful. So this really does represent all machines all at once. Okay. With no warning, we were just in grade year 5, year 6 maths. I want you right now to go to high school maths. Please do 2x squared plus 7x plus 6 divided by x plus 2. No warning, we just left from year 5 to year 11 or something. Please do 2x squared plus 7x plus 6 divided by x plus 2. Let's make this polynomial division right now. Go. No warning, no prep. You're on your own. Whoa, whoa. Can you do it? Can you do it? So this is the lovely thing about teaching maths. It's really about teaching the biggest life skill there is. I've given you a challenge. This is of a very different nature what we've been doing all along. It's scary. I actually wish upon the world that everyone takes part in the 2 fundamental steps of problem solving. There are 2 key fundamental steps of problem solving no one ever seems to talk about. Step 1, when faced with a challenge, with a problem, be your honest human self and acknowledge your emotional reaction. My emotional reaction to this problem is scary. I am scared. Be scared. Maths is created by humans, for humans, to be used by humans. So be human in your relationship with mathematics. If this scares you, be scared. I'm scared. If it delights you, be delighted. If you don't care, be apathetic. Whatever your emotion is, acknowledge it. Step 2, take a deep breath and do something nonetheless. Just do something, anything. Draw a picture of a tree, draw a picture of a fish, maybe draw a picture relevant to the problem, that'd be nice. Read the problem again, turn the page upside down, go for a walk, do something. Because as soon as we can unlock the emotions, if we can work past our emotions and do something, you're probably on the way to understanding the challenge. If we could teach the world the confidence to do something, to get past any emotional impasse you're having, what a gift that would be for humanity. What a gift that would be. And maths, I think, is a perfect vehicle for teaching the confidence to do something. Therefore, I just delayed for a little while because the do something I'm going to do in the remaining 8 minutes and 39 seconds is this. I can at least draw this. Even if this scares the dickens out of me, I've got 2x squareds. I've got 2 of these. I've got 7 x's. I must have 7 of these. And I have 6 of these. I have 6 of these. There, I've at least done something. I've drawn 2x squared plus 7x plus 6. But I can even draw x plus 2. I know it's going to be 1x and 2 1s. It's going to be 1 dot next to 2 dots. Oh, I'm doing division. So I must be looking for x plus 2's in this weird thing. I must be looking for 1 dots next to 2 dots in this picture up yonder. Do I see any 1 dots next to 2 dots? Well, why? Yes. There's 1 dot next to 2 dots. Ooh. Here's another 1 dot next to 2 dots right below. Ooh. Oh, if I go over here, there's 1 dot right next to 2 dots over here. Well, there's another one underneath that. Ooh. And there's another one now. If I think my loop's getting a bit weird now, but very weird loops, but there's another 1 dot next to 2 dots. I see 2 at that x level and 3 at that 1's level. The answer must be, oh, 2x plus 3. Welcome to high school algebra. But here's my real question. Are you experiencing deja vu right now? Does this feel awfully familiar? Because look at the picture we just did moments ago. 276 divided by 12 equals 23 in a 10-1 machine. Look at that picture. Look at this picture. I don't know how to do this. It's the same picture. How do I fit them on my page? No, they're not going to fit on my page. That's so annoying. There it is. There's the same picture. Whoa, whoa. In fact, if I tell you X really was 10 in my head all along, that this really was a 10-1 machine, people seem to forget in algebra class that X can actually be a number. I choose 10 for the number. This will be 2 times 10 squared plus 7 times 10 plus 6. That really would be the number 273. Divided by 10 plus 2, divided by 12, apparently equals 2 times 10 plus 3, 23, which of course it did. It just did it back there. It really is 23. Whoa. High school polynomial algebra is actually a repeat of primary school arithmetic. It's just the lovely abstraction of being able to do it in any base you like, not just being locked into base 10. It is astounding, it's beautiful, it's wonderful. In fact, I think it's time you did one on your ownsies. Try this one all on your own. If you can do this one, life is going to be mighty good for everyone. X to the 4th plus 2x cubed plus 4x squared plus 6x plus 3, all divided by x squared plus 3. Whoa, whoa. Have an emotional reaction to that one. That's crazy. Why do you want to divide that? Good question. If the goal is just to get the answer, I'd type into Wolfram Alpha myself. So it's not about getting the answer. It's not about knowing what the answer is. It's about thinking your way through it. As a logic challenge, can we actually work our way through this beastly thing? Because if we can do this one, I bet we can do any one. It'll probably take us longer just to draw the thing than to actually do it. So I'll start drawing as well. If I'm going to make you work, I should work as well. It seems only fair. Cube squared 3x. Okay. 1 of these, 2 of these, 4 of these, 6 of these, 3 of these. There's the numerator. I'm a little bit nervous about what I'm dividing by, because watch out, it's 1 dot blank 3 dots. 1 blank 3. That blank could be annoying. I wonder how you're going to handle that blank in between the 1 dot and the 3 dots. No pressure, everyone. We only have 4 minutes and 26 seconds left in our lives together. No pressure. So Nadia, if anyone's brave enough to type things in the chat, you'll let me know. Is that right? This is a tricky one.
There are a few people having a really good go at it, James.
Oh, awesome. Love it.
I can see Mark, Diane, Andrew, Paul, they're putting an answer in there.
Brilliant, brilliant.
And someone has just said, can you show us?
Of course I can. The answer is yes. It's always yes. Here goes. Yes. All right, that blank is annoying. So 1 dot, no dots, 3 dots. Here's 1 dot. It seems compelling to do that one. Then I want no dots. I'll draw a loop that actually goes through no dots. 1 dot, 0 dots, and then I want 3 dots. 1, 2, 3. There we go. They must all be there. A lot of explosions. Kaboom, kabow, kabow. A lot of spillage to the left, but they all must have been there to begin with. All right, another 1 dot next to blank 3 dots. So can I do it? I'll do a different color this time. I have a feeling my loops are going to be messy. Can I do this? 1 blank 3. Is that okay? Do a split loop like that? That's really 1, nothing, 3. I guess the answer is yes. The answer is always yes. Because then I can do another one. 1 blank 3. There's another 1 blank 3. Aha! Oh, I can see it now. I can see it. Oh, this is great. What color? Oh, colors choices. It's hard to make color choices under time pressure. Okay, 1 blank 3. another one at that level. Beautiful, beautiful, beautiful. And it's actually 1 at the x squared level and 2 at the x level and 1 at the 1's level. The answer must be x squared plus 2x plus 1. Whoa. And if I make this a grade 5, year 5 arithmetic problem and tell you x is really 10 in my brain all along, I guess we just worked out 10,000, 2,463. So 12,463 divided by 10 squared plus 3, 103 apparently is 121. So there's the grade 5 problem encoded in this high school algebra problem. The power of algebra is that we've actually done an infinitude of problems right there in one fell swoop. That's the power of algebra. In primary school, we learned how to do it specifically for 10, but in high school, you learn to do it for any number you like in one fell swoop, which is actually astounding and powerful and wonderful. Okay, now I'm going to leave you with optional homework because I've been pulling the wool over your eyes a little bit. Copy this one down and try it on your own Z's because I've been avoiding those anti-dots. Here's why I absolutely love teaching polynomial division in high school, because of this challenge. This gives you a serious problem and it's going to cause you some woe. Is there a way around it? Can you figure out what to do? This is the gorgeous moment of polynomial division. How are you going to deal with those anti-dots in there? So step 1, I guess, is draw a picture and then do something. Do something. And when this drives you bonkers, absolutely drives you up the wall, I've got the answer for you. It's at www.globalmathproject. Global Math Project. By the way, that's an American math, so I'm in America, so it's not maths, unfortunately. Mathproject.org /exploding dots. And you'll see everything I did today and more. But when you get to exploration 6, that's where I do polynomial division. And I actually have this very problem in there, and I do explain one way that people have figured out how to handle this and actually get over all the challenges that cause so much grief and woe and just make you want to have a little weep. Have your little weep. Be your honest human self. Cry a little bit. It's okay. Acknowledge it. Take a deep breath and then do something. Just have the confidence to do something. This is the beautiful joy of teaching. However arcane this is in the school curriculum, it matters not, because the content is a beautiful vehicle for teaching life lessons. Welcome to polynomial division. Welcome to exploding dots. And I'm out of time. I guess I've left no time for questions. So that's it. Thank you so much, everyone. Unless Nadia wants to give me like a few moments to answer some questions, I shall. You've been fabulous. Thank you for letting me speak to my homeland. A real honor, a real joy. Thank you.
Thank you, James. On behalf of the MAV, I'd like to thank you very much for your keynote today. I think we all agree there's been a multitude of exploding dots, a few imploding dots, but there's also been an enormous amount of energy and passion coming from you through the screen. It was absolutely so engaging and exciting. The chat was going off with comments like, "This is fantastic. I love James Tanton. I could listen to him all day." So I think it's been a real hit. A few takeaways from me. You certainly made dots very exciting. You certainly covered a lot of ground. Just a personal thank you for going back over some of the primary stuff. Thanks so much. I loved your explanation about why humans were so obsessed with the number 10. Mm-hmm. But I also love your explanation around how the English language is just so weird for our young children learning numbers. So it's a lot for us to take away from that. I'm going to remember 312 T12 for a long time, I think. Excellent. Beautiful. We now know you don't believe in subtraction, and I think you've got a bit of a cult following behind that one. But the mathematics that you did at the end there around that algebra stuff really did blow my mind. So amazing job. Thank you so much. I'd like to thank the Victorian Department of Education for sponsoring your keynote today. If you've got any questions, please let them pop them into the questions down the bottom. Unfortunately, we have run out of time, and I've copied a few over, James, so I'll send them to you as well. Lovely. Thank you so much. We'll now take a quick break. Don't forget to check out the virtual delegate satchel and to touch base with our sponsors and exhibitors throughout the day. The next session in this room begins at 10:25. Thanks, everyone.